a continuation of Earth and Volcanoes, Lecture 1, where we will start by talking about measuring the size of an earthquake. An earthquake occurs when the pressure built up along a fault becomes stronger than the pressure holding the rocks together. Then the rocks on either side of the fault suddenly rip apart, sometimes at supersonic speeds. The two sides of the fault slide past one another, releasing the pent-up pressure. Energy from this separation radiates outward in all directions, including towards the surface, where it is felt as an earthquake. An earthquake's size, or magnitude, depends on how large its parent fault is and how much it has slipped. Because these faults extend from the surface down to several miles deep, geophysicists cannot simply visit the source to calculate these numbers. Instead, they rely on, again, sensors located around the Earth's surface, which measure seismic waves, or vibrations from an earthquake. Prior to 1935, the estimation of the intensity of an earthquake was based on a qualitative and subjective interpretation of Mercalli intensity. You can see, for example, Exploring Geology for more information. Charles Richter from Caltech devised a quantitative method based on the largest amplitude of the waves recorded on a seismogram. The Richter basic idea is that the size of the amplitude depends on the distance station focus, the intensity or magnitude of the earthquake. Large amplitudes in the seismograms imply either that the earthquake epicenter is very close to the recording station, or that the earthquake is far away from the station, but very large. Here is an illustration of how to measure the maximum amplitude, which is the S wave's maximum amplitude. In this example, the maximum amplitude is about 23 millimeters. Here is how the Richter scale works, by using a graphical device known as Richter's monogram. Given a distance station epicenter and the maximum amplitude in millimeters, measured on a seismogram, we can determine the magnitude of the earthquake. Here are some examples. Given a station epicenter distance and the maximum amplitude in millimeters measured on a seismogram, we can determine the magnitude of an earthquake, as we mentioned before. By using this monogram, an earthquake of magnitude 5 on the Richter scale at a 100-kilometer distance would have an amplitude of 100 millimeters, as shown here by the blue line. An earthquake of magnitude 4 on the Richter scale at a 100-kilometer distance would have an amplitude of 10 millimeters, as shown here by the green line. An earthquake of magnitude 3 on the Richter scale at a 100-kilometer distance would have an amplitude of 1 millimeter, as shown here on the red line. This last example represents the standard Richter earthquake. This standard earthquake is 100 kilometers away from the recording station and produces 1 millimeter of amplitude on the seismogram. Let's repeat this description. Again, suppose that we have a 100-kilometer distance between the station and the epicenter, and a 100 millimeter maximum amplitude from the seismogram. We then get a magnitude 5 for this earthquake by using the Richter scale. Suppose now that we have a 100-kilometer distance between the station and the epicenter, and a 10 millimeter maximum amplitude from the seismogram. We get a magnitude 4 for this earthquake by using the Richter scale. Suppose now that we have a 100-kilometer distance between the station and the epicenter, and a 1 millimeter maximum amplitude from the seismogram. We get a magnitude 3 for this earthquake by using the Richter scale. Here are 3 different recordings of this same earthquake at 3 different locations. These 3 recordings will produce the same magnitude. For your Richter recordings, the parameters are an SP time of 49 seconds. The station epicenter distance is at 480 kilometers, and the amplitude is 280 millimeters. For Las Vegas recording, the parameters are the SP time of 64 seconds. The station epicenter distance equals 600 kilometers, and the amplitude is 100 millimeters. For Elko's recording, the parameters are an SP time of 72 seconds. The station epicenter distance is 690 kilometers, and the amplitude is 60 millimeters. Again, remember that the SP time is the elapsed time between the arrival of the first P wave and the first S wave for a given seismogram. These 3 recordings produce the same magnitude, as we can see here. In fact, recording stations are supposed to produce the same magnitude for a given earthquake, no matter their distance from an earthquake's epicenter. Notice that the magnitude of earthquakes, or more specifically, microearthquakes, can be negative. For example, an earthquake with an amplitude of 0.01 millimeters at a 10-kilometer distance from the seismic recording station will have a magnitude of -1. With the highly sensitive sensors available today, one can even record earthquakes of -2 magnitude. This order of magnitudes is common in microseismicity. In fact, typical microearthquakes induced during the hydraulic stimulation of a shale gas reservoir are of magnitudes -2 to -4. Let's try to understand what these magnitudes mean. Each unit of increase in earthquake magnitude corresponds to a 10-fold increase in amplitude seismic signal. A magnitude 7 earthquake is 100 times larger than a magnitude 5 earthquake. A magnitude 9 earthquake is 10,000 times larger than a magnitude 5 earthquake. Each unit of increase in earthquake magnitude corresponds to roughly a 32-fold increase in the amount of energy released. So, the energy of a magnitude 9 earthquake is over 1,000,000 times the energy of a magnitude 5 earthquake. This table shows the standard classification of earthquakes. Earthquakes with magnitudes less than 3 occur every day and are generally not felt by people. An earthquake of magnitude 3 to 5 is considered minor, whereas a quake with a magnitude of 5 to 7 is moderate to strong. At the higher end, these quakes can be destructive to cities. Earthquakes from 7 to 8 are major. About 15 of these occur annually. Every year, at least one earthquake with a magnitude over 8, a great quake, wreaks havoc. An earthquake with a magnitude of 10 has never been measured, but it would create widespread devastation. Let us reiterate. A magnitude less than 3.5 is generally not felt, but recorded. A magnitude of 3.5 to 5.4 is often felt, but rarely causes damage. A magnitude of 5.4 to 6 is at most slightly damaging to well-designed buildings. A magnitude 6.1 to 6.9 can be destructive in areas up to about 100 kilometers across where people live. A magnitude 7 to 7.9 can cause serious damage over larger areas. And a magnitude 8 or greater can cause serious damage in areas several hundred kilometers across. Every year, at least one earthquake with a magnitude over 8, or a great quake, wreaks havoc. An earthquake with a magnitude of 10 has never been measured, but it would create widespread devastation. There are usually small earthquakes before and after the main quake. The earthquakes before the main quake are known as foreshocks. The earthquakes after the main quake are known as aftershocks. An aftershock is a smaller quake that occurs after a previous large quake in the same area, or the main quake. If an aftershock is larger than the main shock, the aftershock is redefined as the main shock, and the original main shock is redefined as a foreshock. The foreshocks can precede the main shock by days or so, in some cases by as much as several years. Aftershocks are smaller earthquakes formed as the crust around the displaced fault plane adjusts to the effects of the main shock. Let's talk about the other earthquake magnitude scales. Scales other than the Richter scale are used these days, such as the moment magnitude scale, to provide a better idea of the shaking and possible damage from earthquakes of all kinds around the world. Here is the general formula of all the earthquake scales out there. A is the amplitude of the signal. T is its dominant period. F is a correction for the variation of amplitudes, with the earthquake depth and distance from recording stations. And C is a regional correction. By selecting a particular wave, that is, body or surface wave, this formula allows you to construct a new scale through the parameter A, which is the amplitude of the signal. For example, MB is the earthquake magnitude based on body waves, and MS is the earthquake magnitude based on surface waves. Similarly, we can use the dominant period, the correction terms, to construct new earthquake magnitude scales. We can deduce Richter scale from the general formula by assuming that the dominant period T is 0.8 and that earthquake depth H is almost constant. We can also select the regional constant C for Southern California. So the Richter scale is as follows. Using the largest amplitude of surface waves, we can define the surface wave magnitude as follows. Using the largest amplitude of body waves, we can define the body wave magnitude as follows. A more consistent measurement of big earthquakes nowadays is the magnitude calculated on the basis of seismic moment, called moment magnitude. Because fault geometry and displacement are a part of the seismic moment, the moment magnitude is a more consistent measure of earthquake size than is magnitude. And more importantly, moment does not have an upper bound. Seismic moment equals rigidity times fault area times slip distance. By using the seismic moment, here is moment magnitude formula. Note that no matter how big the earthquake MB never exceeds 6.4, and MS never exceeds 8.4. However, MW is defined by the moment, so it never saturates. Let's look at this example. Here, the fault length is 100 kilometers. The fault depth has a minimum of 12 kilometers. The average slip is 6 meters. The average rigidity is 3 times 10 to the 11th power, 9 centimeters squared. The seismic moment equals 2.16 times 10 to the 27th power. You'll get a magnitude of 7.5. Now it's time for a quiz. Calculate the moment magnitude based on the parameters described in the previous slide with an average slip of 8 meters. Define P waves, S waves, and surface wave arrivals of the following seismic recording. Now we'll give you your answers. When we asked you to calculate the moment magnitude based on the parameters described in the previous slide with an average slip of 8 meters, this is what we'll do. We just replace 6 by 8 in the seismic moment formula to a moment magnitude of 7.6. Seismic moment equals 2.88 times 10 to the 27th power. This gives us a moment magnitude equaling 7.6. When we asked you to define P wave, S wave, and surface wave arrivals of the following seismic recording, here's your answer below. Now let's talk about the source mechanism. From recordings of earthquake-generated waves, we want to get as much information as possible about the earthquake source, including the hypocenter, or latitude, longitude, and depth, the origin time, the start time of the earthquake, the magnitude, or the size of the earthquake, and the focal mechanism, the faulting type and size. We have not discussed the focal mechanism yet. This is our next task. In our description of focal mechanisms, we assume that seismic energy is radiated from a planar surface across which relative motion occurred during an earthquake. Geological observations of faults that reach the surface, suggests that this is a good approximation in many cases. Moreover, this assumption is generally, but not always, consistent with seismic data. This figure defines the terms hanging wall, footwall, strike, dip, and slip used in the focal mechanisms. The block above the inclined fault surface is the hanging wall. By contrast, the footwall is the block below the fault surface. The slip vector characterizes the motion of the hanging wall relative to the footwall. This figure shows with positive slip along hanging wall, footwall, strike, dip, and slip used in the focal mechanisms. The geometry of a fault is described in terms of the orientation of the fault plane, that is, surface or zone across which there is shear displacement, and the direction of the slip along the plane. The fault plane is characterized as its normal vector, or N, and its direction of motion is given by D. The slip vector is in the fault plane. The slip vector indicates the direction in which the hanging wall, or the upper side, moves with respect to the footwall, or the lower side. The slip vector always lies in the fault plane and is therefore perpendicular to the normal vector N. Here are the key parameters of a fault plane. Delta is the slope angle of the footwall block measured clockwise from horizontal. It varies from 0 to 90 degrees. Phi is the direction of the surface intersection of the fault measured clockwise from north. It varies from 0 to 360 degrees. Lambda is the direction of fault movement measured counterclockwise from strike and slip direction. It varies from negative 180 to 180 degrees. These angles are related to normal vector of the fault plane and the slip vector in the fault plane through these formulas. Here are the three types of fault geometries with their slip angles. Notice that we included the strike-slip fault twice to differentiate a left lateral strike-slip fault from the right lateral strike-slip fault. Let's now introduce two representations of the parameters of fault geometry that are used in earthquake studies. These representations are known as focal mechanism diagrams, or focal mechanisms. These representations offer an alternative way of representing types of fault geometries without drawing footwalls. And more importantly, they are directly related to seismic data associated with earthquakes. We start from the 3D image of the fault plane, as illustrated here. We can construct a plane in a sphere based on the strike angle and the dip angle. This is a nodal plane. We can construct our second nodal plane, which is perpendicular to the first nodal plane, by using the slip angle, as illustrated here. This figure shows a spherical representation of the fault geometry with two nodal planes. One of the two nodal planes represents the orientation of the fault plane that generated the earthquake. The other is the auxiliary plane that is perpendicular to the first nodal plane. The auxiliary plane represents the direction of the earthquake slip. Again, we have two nodal planes. One of the two nodal planes represents the orientation of the fault plane that generated the earthquake. The other is the auxiliary plane, a plane perpendicular to the line describing the direction of slip in the earthquake. This line must lie on the fault plane. We will now construct a 2D version of the sphere of nodal planes. As illustrated here, we divide the spherical representation into two hemispheres. The 2D projection of the lower hemisphere provides a 2D representation of our fault geometry. This 2D representation is called a focal mechanism diagram, or simply a focal mechanism, and it is sometimes called a seismic beach ball. Here are the two typical fault geometries introduced earlier with their focal mechanisms. Notice how the focal mechanisms simplify the representations of fault geometries. We no longer need footwall blocks. Moreover, the fault plane that generates the earthquake, along with the perpendicular auxiliary plane, is captured by the focal mechanisms. In other words, we can describe the faulting type of earthquakes by simply examining its focal mechanisms, which define the type of faulting that occurs during an earthquake. Here are another two typical fault geometries, introduced earlier with their focal mechanisms. Again, notice how the focal mechanisms simplify the representations of fault geometries. We no longer need footwall blocks. Moreover, the fault plane that generates the earthquake, along with the perpendicular auxiliary plane, is captured by the focal mechanisms. In other words, we can describe the faulting type of earthquakes by simply examining its focal mechanisms, which define the type of faulting that occurs during an earthquake. Note that in many cases, earthquake source mechanisms involve striking orientations different from the ones introduced so far, and even some combinations of strike-slip faulting and normal or thrust faulting. This figure shows some of these cases, along with focal mechanisms. In other words, the fault mechanism representation is valid, even for very complex cases. Now let's talk more about construction of focal mechanisms from seismic data. Seismic waves radiating from earthquakes carry information about the geometry of the fault and the motion they experience during rupture, because the patterns of radiated seismic waves depend on the fault geometry. An analysis of seismic recordings of an earthquake allows seismologists to determine its sense of slip, even if the rupture does not reach the surface, by using data from many stations. Let's repeat this. Seismic waves radiating from earthquakes carry information about the geometry of the fault and the motion they experience during rupture, because the patterns of radiated seismic waves depend on the fault geometry. An analysis of seismic recordings of an earthquake allows seismologists to determine its sense of slip, even if the rupture does not reach the surface, by using data from many stations. In other words, seismic data can be used to obtain a clear picture of a focal mechanism. For example, the analysis of first motion, or of P waves, can be used to infer the focal mechanism. based on the idea that the polarity of the first P-wave arrival will vary between seismic stations at different directions from an earthquake. These variations occur because the first motion is either compressional, material initially displaced toward the station, or dilational, material initially displaced away from the station. Examples of first motions from a pure strike-slip earthquake are shown here. The polarity of initial P-wave pulse form an earthquake which is compressional, or up and pushed, or dilatational, or down and pulled. This figure illustrates the first motions from a purely strike-slip fault earthquake. From this picture, we can easily recognize the link between polarities of seismic events and focal mechanism. Seismograms exhibit small or zero first motions in the directions of nodal planes because the first motion changes from dilatational to compressional. So we can find the orientations of nodal planes from the first motions of P waves. Therefore, the fault geometry is known. However, first motions alone cannot distinguish between the fault plane and the perpendicular auxiliary plane. Notice in principle that we could use any events in seismic data, that is, S, PP, and PS, to determine nodal planes. But only first P-wave arrivals have been used so far, because the later arriving events are more difficult to identify because of interferences between events. The following are the practical steps for estimating a focal mechanism. You must first determine polarities of P-wave first motions. Then you'll compute the azimuth and takeoff angle for all available stations. Plot the information of P-wave polarities on the equal area projection chart. Then you'll select the nodal planes. Let's now expand on each of these steps. In step 1, we have to determine the polarities of the P-wave first motions by checking the waveforms recorded by various seismic stations in the area. And then we have to mark the first arrivals as up, or compressional, or down, or dilatational. In step 2, each station's location relative to the hypocenter is then projected onto our circular diagram with a symbol representing the type of motion, up or down, first recorded there. We need to compute source-receiver azimuths and the takeoff angle at the hypocenter in order to properly locate the stations in the sphere. This figure shows the azimuthal angle from source to receiver. This figure shows the angle from the vertical axis from which the ray leaves the earthquake, which is the takeoff angle. It can then be calculated by using the distance between source and the receiver location. With the azimuth from source to receiver and takeoff angle, we have a unique point on the sphere around the focus. An example of first motions is shown here. The pattern of compressions and dilatations are mapped onto the sphere corresponding to source-receiver pairs, or azimuth and takeoff angles. Fault plane solutions for first motion studies are now added to first motions in this picture. This is a pure strike-slip earthquake. Again, we need to plot the first motions recorded from our earthquake. To do this, we check the waveforms recorded by various seismic stations in the area and mark the first arrivals as up or compressional, or down or dilational. Each station's location relative to the hypocenter is then projected onto our circular diagram with a symbol representing the type of motion, up or down, first recorded there. Stations that fall within the missing upper hemisphere, or above the horizontal, are translated appropriately onto our lower hemisphere projection. In step 3, once the first motions are correctly plotted, it is time to solve for the two nodal planes. The sphere is divided into quadrants using two perpendicular planes that best fit the set of first motions. Again, since the two-dimensional plot shows only the projection of the inner surface of the lower hemisphere, those planes will look like two intersecting lines within a circle. In step 4, after the nodal planes have been identified, the focal mechanism is complete. But it is of somewhat limited use because either of the two nodal planes could be the fault plane. Other types of data can be useful in determining which plane is the fault plane, and consequently what type of slip occurred in the earthquake. Knowing the geology of the area will help identify the most likely fault geometry. Aftershocks can also be of great assistance because their sequences can provide valuable hints about fault plane orientation, based on the idea that aftershocks occur around a fault plane, and therefore can show the direction of a fault plane. Though not always feasible, these insights can lead to a final determination of the fault plane solution. In summary, fault plane solution using P-wave polarities includes the following steps. You must determine polarities of P-wave first motions. You must compute azimuth and takeoff angle for all available stations. You must then plot the information of P-wave polarities on the equal area projection chart. Then you can select the nodal planes. This example shows a selection of focal mechanisms for some of the largest earthquakes in Cascadia subduction zone. The Cascadia subduction zone stretches from northern Vancouver Island to Northern California. Now it's time for a quiz. Please associate each of the block diagrams below with one of the fault mechanisms also illustrated below. Here are the block diagrams. Here are the focal mechanisms. This is the answer that correctly associates the diagram with the block mechanism. Thank you for listening to this iMode Education lecture. Remember, there is a large selection of iMode Education lectures, which can further enhance your knowledge of earthquakes, volcanoes, climate, and energy.